So now we are on forces and moments in machines, lecture 4, lecture 3. Okay. We have looked at balancing of rigid rotors so far, and there is one last part that we have to tie up in that. So here we have the x-axis, here we have the y-axis, here we have the z-axis, here in blue we have the rotor, it has a center of mass. As I have discussed, with a couple of masses it can be brought to this z-axis even if it is not. So we will temporarily think about this as being on the axis. On the axis is static balance. Static balance, and then when we check for moments, that is dynamic balance. I will send you a PDF problem where this center of mass will be off the axis, but it is simplest for now to think of it as on the axis. Now over here in green, I am marking some plane which we will call plane A. Maybe here, this is plane A, and over here there is another plane, that is plane B. And as we have discussed so far, over here at some distance d, we can put one mass, and then over here rotate it at some other distance d, at also distance d, but along the y we can put a mass. This mass will be max, this mass will be may, and I pointed out similarly we will have bx, by, this distance being d, this distance being d. I pointed out that this max does not appear by itself, it is always multiplied by the distance, so we can double the distance and make the mass half, and the effect on balance will be the same. There was another interesting point, which is that this ma and this max and this may can be combined vectorially. So max di plus may dj is taken as some m effective r vector like that. That is that vector r. If we choose the magnitude of r to be equal to d, then it is easy enough. What happens is this one is taken as some m, that is that capital M. This angle would then be phi. M cos phi would be this max. M sin phi would be this may. I hope you remember this from the previous lecture. So really the point, then the conclusion is that really we may just have to add some mass here and maybe some other mass at some other angle, maybe here, and then we would have both static and dynamic balance. Now, in terms of what these masses are, I showed you 4 equations. 4 unknowns. And then I discussed the principles of balancing in the field, that is an experimental application of balancing. This is where we are coming now. So by this I mean experimental, actually balancing it, not doing calculations. All right. So what I pointed out is that on your rotor you need some kind of reference line. So you have a reference line here. This line is going around. If the rotor is going at a speed omega, angular speed omega, then this line later is at an angle theta, and theta is equal to omega t. Okay. All right. Now let us say that we have a means of locating this line. So how would we do that? For example, we have a reflector tape here, right? And then we have a light source here, and we have a camera here. So if it could be other things, right? It could be that there is a little protuberance over here and I have a proximity sensor, so that measures it every time it goes past. Okay, whatever it may be, but let us think about it like this. This is a concept only, but you understand that I have something which will give me a signal every time this line goes past. Now on my time axis, the output from this reflector will be, the camera output may look like this. And so on. And then what happens here is, from here to here I have a 2 pi rotation of the shaft or rotor. Okay, so I draw this line here, I draw this line here. If I don't think of this as time, but if I think of phase or rotation, then this distance is 2 pi. Okay, I can also, if I want, think of time as starting from here, and then I can think of this axis as omega t, then omega t goes from 0 to 2 pi. I hope you understand that this is how am I seeing this? Maybe I am seeing this on an oscilloscope. Okay, all right. In addition, now I have a vibration measurement, right? So that vibration measurement can be done in any way, but for example, if this was plane A, then on plane A, corresponding to this over here, maybe I have an accelerometer. Okay, so now the accelerometer signal, now let's say that this is the 0 line for that accelerometer signal. Now, and the accelerometer signal might be like this. Little bit here, little bit here, little bit here. Let me okay, so this is the acceleration signal in plane A. All right, now I will locate this maximum. Let us say I locate this maximum over here, and I will call this angle. Previously I had called it phi, but I want to avoid confusion because over here I have called this angle phi. So over here, let me come in here and let me call this angle psi A. Okay, and let us say this amplitude, let me call that I need to give it a name. So there was a plane A, let me call this A bar. Okay, so this vibration signal is now A bar, and let's see now, cosine of omega t minus psi A. Alright, so this is the state of vibration that you are observing in this system as it is spinning because of the unbalance that is there. If it was perfectly balanced, you would get no vibration here. In reality, in an experiment, you would get some vibration, but over here, in theory, you will not. And in experiment, if it is small enough, you will say that it is balanced. Okay. Now, similarly, there is a plane B. And on plane B also, let us say in the same location, for simplicity, I have another accelerometer. And this is going to give me another signal, which again I will see on an oscilloscope. So notice that on the oscilloscope, suppose I have a dual trace oscilloscope, which is very basic. I could have multi-channel data, but if I have a dual trace oscilloscope, then first I can measure this green signal, which is from the reflector tape, and the blue signal, which is the accelerometer in plane A. And separately, next time I can again measure the green signal and a yellow signal for the accelerometer in plane B. Okay, so when I do that, it will have some other value. Let me assume for the moment that it passes through here and passes through here and passes through here, and let us say it's a bit bigger. These pictures were not very good in my last video, and I'm trying to correct that and clarify. Okay, so here, now let us say that this distance here is psi b. Okay, and let us say this height here is b bar. In that case, I will have acceleration signal in plane B will be b bar cosine omega t minus psi b. Okay, so when omega t is 0, then I am behind, but when omega t has become equal to psi b, that means when omega t is here, that is when the cosine is maximum, it is b bar. Okay, so I have this measurement and I have this measurement. I want them both to be 0, and I want to do that by adding masses. As I have discussed, we can do this by adding 4 masses, but that is in calculation. In the experiment I described, we can do this with 4 masses, but that is actually more experiments than we need. In principle, we can do it with fewer experiments, and that is what I want to show you now. To do that, I will demonstrate, because I am here with the yellow already, I will demonstrate with this. Okay, now let us say that I add, let me come here. Let us say that for balancing purposes, I add in plane B over here, I add a mass at some location, right? So now this is some other angle. So for simplicity, let me first think of adding it. Remember, this is on the rotor. I'm showing it yellow, but it is on the rotor. Let me add it lined up with that reference line. So when the reference line is vertical, let me say I put a mass over here. Let me say that distance is d. Let me say this mass is mb x. Okay, so that is the trial mass that I have put here. This is a trial mass. All right. I come here. What happens is I get with trial mass mbx. What I get is a new one. See, I get b bar new cos omega t minus psi b new. But using trigonometry, you know that this is the sinusoid, this is another sinusoid, the difference is the sinusoid. So I will actually write it as b bar cos omega t minus psi b plus delta b due to the mass mbx, right? So let me call it delta b1 cos omega t minus psi b1. What I want you to understand is this is the old vibration measurement. This is that phase relative to the rotor's main time marker. This is the state of the unbalanced rotor. This is the measurement after the experiment. This is the change in the vibration state. This change in the vibration state has its own magnitude and its own phase. This is a measured quantity. These are measured. Okay, so these are measured. Okay, because they are measured, this change is supposed to be only due to mbx. Okay, all right. There is one minor complication, which is that when I add mbx, this is going to change too. So this is going to change to a bar cos omega t minus psi a plus delta a1 cos omega t minus psi a1. And I emphasize that this one and this one are measured. This is the vibration before adding this trial mass. With the trial mass, mbx, there is a change in the vibration observed in both planes. There is a change in both planes. Where is it? Here. There is a change in both planes, here as well as here. Okay. All right. So now we come to the last part. The last part I will write in green. In this experiment, in this experiment, instead of adding the trial mass mbx, suppose I had added a trial mass mby, then physically we expect that the change in the vibration will be exactly the same, only assuming the rotor is like this, it will occur pi by 2 in advance, right? Because this mass will just be the same as that mass appearing in advance. This is why when if same mass was placed along y as mby, then pi by 2 would be added here, plus pi by 2. This would not change. Psi b1, let me make it fatter so that you understand. Let me make it maybe green. This one will not change. Cosine will stay cosine, omega t will stay omega t. Psi b1 is what it was, plus pi by 2. Okay. In this way, for this reason, the experiment with this mass is not really needed. Okay. So the experiment with this mass is not really needed, and so what I had said earlier, we are doing basically an experimental version of Newton-Raphson. So we put MAX and measure change in both planes, vibration measurement, and then we put MAY and then we measure, but actually this second measurement is not needed because it is a rotating system. This one tells us what that is, and then we have to do an MBX, and we don't need to do MBY. Of course, you can do both for checking consistency. You can do both to check consistency, but we won't need it. So we will still solve. You see, each one will give us effectively two measurements. That part is from theory. From theory, we will know that this and that one are related. They are related as I have explained over here. And then after that, we solve our equations.